So, in the last class we looked at calculating the exit static state from the nozzle. What we need to do is to calculate both the specific thrust or the thrust produced by the engine as well as the fuel consumption for the engine. So, the exit static state from the nozzle will allow us to calculate the thrust produced by the engine. What we are going to do in this class is to evaluate the fuel consumption for the engine. So, the fuel consumption for the engine can be obtained by doing an energy balance for the combustor. Okay. So, if you look at the combustor at steady state operation, so we have mh dot amount of air coming in at a stagnation temperature T03, and we have a certain amount of fuel mf dot which comes in with negligible velocity, but with calorific value given by this amount. So, this is the rate at which energy is being brought into the combustor by the fuel, right. This is what happens for the fuel, and the exit stream has mass flow rate mh dot plus mf dot times Cp gas times T04. This is the exit stagnation temperature. Okay. Remember, T03 we have already calculated from the given overall pressure ratio for the combustor, and T04 is actually prescribed as the maximum allowable temperature in the cycle. So, the turbine entry temperature is given to us, and once again mh dot plus mf dot is usually not mf dot is negligible when we add to mh dot. So, we keep that in mind, but notice that here we cannot ignore mf dot here because H fuel is a very large number. If you remember, H fuel is 45,000 kilojoule per kilogram. So, it is a large number. So, that multiplied by mf dot will still be a very big number. So, we cannot neglect this. If you neglect this, then this equation will become meaningless. That also is an indirect check of this equation. So, the ideal amount of mass fuel flow rate that I need to provide then comes from this equation. Okay. Notice that here I have neglected mf dot in comparison with mh dot. This I am allowed to do because mf dot is usually a much smaller number compared to mh dot. That I am allowed to do. So, I can rewrite this equation for the mass flow rate of fuel as something like this. Okay. So, this is the amount of fuel that I need to burn to take a stream of air from a stagnation temperature T03 to a stagnation temperature T04 under ideal conditions. Okay. But as we discussed earlier, when I burn a certain amount of fuel in a combustor, there are going to be losses. Some of the heat goes towards increasing the temperature of the combustor components, some is lost to the ambient air. So, there are a lot of losses, right. So, there are a lot of inefficiencies. So, I account for that by saying that this is the amount of fuel I need to burn under ideal circumstances. So, in the actual circumstance, the amount of fuel that I burn is going to be the ideal value divided by the efficiency of the combustor. So, this is going to be more than the ideal value, understandably. Right. So, this gives me the actual mass flow rate through the combustor. Okay. So, given a value for eta combustor, I can calculate this, I know this, I can calculate mf dot actual. Okay. So, this allows us to calculate the thrust and the mass flow rate, from which I can calculate the specific thrust and the thrust specific fuel consumption. Okay. So, we are now ready to proceed with our calculation for a particular example. So, for the worked example, I have chosen the following engine. The CF6-50C2 turbofan engine is a mid-size engine, right, manufactured by GE Snecma, and it has the following specifications: bypass ratio 4.31, fan pressure ratio is given 1.7, overall pressure ratio is given, air mass flow rate, and the turbine entry temperature is also given. Okay. The component efficiencies for the inlet, for the fan and the compressors, right, turbine, the nozzle, and the mechanical efficiency is given. There is a 5% loss of stagnation pressure as shown here. Okay. So, the properties as we listed earlier, the properties also need to be given, right. We have already discussed that. So, for air we will use a certain value for gamma and Cp, and for the combustion gases we will use a certain value for gamma and Cp. So, I will let you write down these numbers, then we will go to the next slide. where the property values are given. So, here the performance, the metrics and the efficiencies are given here. Okay. So, the properties are given here for air, Cp and gamma are given, combustion gases, calorific value of fuel is also given here. We are asked to determine the thrust specific fuel consumption and the nozzle exit areas, both the cold and the hot nozzle, for the following condition. Okay. Two conditions are considered. One is the static thrust, meaning the engine is on a test stand, Va is equal to 0, Pa is equal to 100 kPa ambient condition, Ta is also equal to ambient temperature 25 degrees Celsius. I am sorry, this corresponds to 15 degrees Celsius, correct? Yes. Relatively cold day. And then we are also asked to calculate the thrust, TSFC and nozzle areas for cruise at 10 km altitude, which corresponds to running conditions of 0.8 for the Mach number, ambient pressure 26.5 kilopascal and ambient temperature 223 Kelvin. Okay, so, we are asked to calculate this for both these conditions. Notice that the nozzle that we use in an aircraft engine like this CF6 engine, the nozzle area is fixed, it is not a variable area nozzle, it is not an afterburner nozzle. The nozzle area is fixed. So, you must keep in mind that the nozzle exit areas will be the same for static and cruise conditions, it is not going to change. But that is an important factor that we must use during our calculations. Okay. So, now we start the step by step procedure. We start from the static state A, we evaluate T01 P01, T02 P02, T03 P03, T04 P04 and then T05 P05, T06 P06. Once we have that, then based on T06 and P06 we can calculate PEH and VEH for the hot nozzle. Now, based on P02 and T02 we can calculate PEC and VEC for the cold nozzle, then we can do the thrust calculation. That is going to be our strategy. Okay. Let us start. So, let us first do the calculations for static conditions. So, it is given that Va is equal to 0. So, that means P0A is equal to Pa is equal to 100 kPa and T0A is equal to Ta is equal to 288 Kelvin. So, this is the free stream condition. So, at entry to fan, this is the inlet. So, at entry to fan, since there is no work or heat addition or extraction in the inlet, we have T01 is equal to T0A is equal to 288 Kelvin. And P01 at the end of the inlet was equal to Pa times 1 plus eta inlet times T01 over Ta minus 1 raised to the power gamma minus 1. So, eta inlet is known, all the other quantities are known. So, if you plug in the numbers, right, the fact that T01 is equal to T0A and the fact that T0A is equal to Ta makes this term 0. because we are looking at static test conditions. T01 is equal to T0A and T0A equal to TA, so this goes to 0. So in fact this stagnation pressure P01 also comes out to be 100 kPa. This makes sense, right, because the air is not moving, so the inlet cannot take a static air and increase its pressure. The inlet is designed to take the air that is moving and convert some of the momentum to static pressure. In this case the air is not at all moving, so there is no question of taking the air and increasing its static pressure. So this number makes sense. So our definition for the isentropic efficiency of the inlet seems to be consistent. It works fine, right. So that is P01 and T01. So we know the entry conditions at the inlet to the fan. So we know P01 and T01. Next we have to determine P02 and T02. So at the fan exit, P02 is equal to P01 times the fan pressure ratio. This was how the fan pressure ratio was defined. So P02 is equal to P01 times fan pressure ratio. And if I substitute the value for fan pressure ratio, let me just go back here a little bit. So the fan pressure ratio is given to be 1.7. So that means P02 is equal to 100 kilopascal times 1.7. So this is 170 kilopascal. So we know P02. Now we can evaluate T02 from the thermodynamic, from the expression for isentropic efficiency for fan and the isentropic relationship itself, right. So T02 is equal to T01 times 1 plus 1 over eta fan times fan pressure ratio raised to the power right. You may recall that this, or I am sorry, this quantity inside, remember, comes from, this is nothing but T02S, and then we use the isentropic efficiency of the fan to calculate T02, right. So we had P02, so that means once I have P02, I know P02S. Once I know P02S, I can actually calculate T02S, right. State 02S and 02 are on the same isentrope. So once I know P02S, I can calculate T02S. Once I know T02S, I can use the definition of the isentropic efficiency of the fan to calculate my T02, and that is what I have done here. Okay. So from this you can also calculate P02S and then calculate T02S and then calculate T02, right. That is also okay. So if you substitute the numbers here, then you should get T02 to be 339 Kelvin. Would you prefer to do these calculations that way rather than doing these expressions? Is that better? The P02S, T02S, is that better? Or this is okay? This is alright. This seems to compress too many of the things into this, that is the only thing. But in an actual calculation, it is probably better to do this using the P02S expressions that we have written down earlier. Okay, so now we have P02 and T02. So let us go ahead and complete the fan nozzle also. For the fan nozzle, once I know P02, I can calculate the critical pressure for the fan nozzle. So, for the fan nozzle, PE critical is equal to the upstream stagnation pressure P02 times 1 minus 1 over eta nozzle times gamma minus 1 over gamma plus 1, and if you substitute the numbers, you get this to be 87.88 kilopascal. That is PE critical for the fan nozzle. The ambient pressure is given to be, since PA is equal to 100 kilopascal for this case, which is greater than the PE critical. This means that the cold nozzle is not choked. Therefore, the exit static pressure for the cold nozzle PEC is equal to the ambient pressure, and that is equal to 100 kilopascal. Yes. Oh yes, thank you. So this has gamma over gamma minus 1. Yes, thank you. So please include that also. So there is an exponent here, gamma over gamma minus 1. So I know the exit static pressure, I need to evaluate the exit velocity or the exit static temperature, any one of those things would do. So let us calculate the exit static temperature. Remember, once I know the exit static pressure in the fan nozzle, PE, PES is equal to PE because they both lie on the same isobar, then I know the stagnation quantities at the inlet. I know T0 at the inlet to the nozzle, I know P0 at the inlet to the nozzle. Now I know the static pressure PES, which means I can evaluate TES using the isentropic relationship, right. So once I have TES, then I can evaluate TE at the exit to the nozzle. So let us see how we go about doing this. So TEC is equal to T02 times 1 minus eta nozzle times 1 minus PEC over P02 raised to the power gamma minus 1 over gamma. That is what we have done here. So once I know the exit static pressure, we outlined the calculation procedure. Once I know the exit static pressure, I know PES, I can evaluate TES. Once I evaluate TES, I can evaluate VES square over 2 Cp, and then I can evaluate VES, or I can also evaluate the static temperature and then go from there. Okay. Remember the expression for nozzle efficiency itself, right, the expression for nozzle efficiency, we wrote this down as T0 minus TE divided by T0 minus TES, correct. This was what we wrote down the expression as, and if you use the definition for stagnation temperature, you can see that this can be written as VE square over 2 Cp divided by VES square over 2 Cp. So once I know my PES, I know T0, I know P0. I can either evaluate TES from this expression, or I can directly evaluate VE from this expression, VES square and then VE from this expression, both are okay, and that is what I have done here. So, if I go ahead and substitute the numbers, I get the static temperature TEC to be, the static temperature at the exit of the coal nozzle to be 293 Kelvin. And so, the velocity at the exit VEC comes out to be square root of this quantity, and that works out to approximately 305 meter per second. So, now I can calculate the fan thrust. Remember, the fan nozzle is not choked, so PEC is equal to PA, which means the pressure thrust is absent, we have only the momentum thrust. So, the thrust from the fan comes out to be m dot C times VEC minus VA, and VA itself is equal to 0 because the engine is on a static thrust stand. And m dot C is nothing but B over B plus 1 times m dot, right, that is the amount of air that goes through the fan. So, this times VEC, okay. So, I know B, I know m dot, the total mass flow rate. So, I can calculate the fan thrust to be 166 kilonewtons. So, this takes care of the fan stream completely. Now, we need to do the calculations for the core engine stream. Okay, let us do that next. So, for the core engine stream, so I start with the compressor outlet. So, this is the HP compressor, if you remember. So, this is the HP compressor. So, P03 is equal to the pressure ratio RP times P01. Remember, the pressure ratio itself is defined as P03 over P01. So, I can calculate this to be 30, P01 is 100 kPa. So, I can calculate this to be 3040 kilopascal. So, once I know P03, I know P03S, right, and I can calculate T03S. Let us go ahead and do it that way. So, please calculate. So, P03S is equal to P03. So, which means that T03S is going to be, what is this going to be? We use the isentropic relationship to calculate T03S. So, calculate, please calculate and tell me what T03S is. So, as shown here, T03S is going to be T02 times P03S divided by P02 to the power gamma minus 1 over gamma. So, if you substitute the numbers, what do you get for T03S? Seven 772 Kelvin. Okay. Now, the efficiency of the compressor, if you recall, the efficiency of the compressor is given as T03S minus T02 divided by T03 minus T02. Now, I know efficiency of compressor is given, T03S is known, T02 is known. So, I can calculate T03 from this expression. So, if I go ahead and do that, what do I get for T03? The efficiency of the compressor is given to be 0.92. Yes, I have about 811 Kelvin, okay, that is close enough. Okay, good. Let us go to the next one. At the combustor exit, T04, the maximum temperature is given. So, T04 is given to be 1500 Kelvin, and P04 can be evaluated like this. P04 is equal to P03 times 1 minus delta P naught of the combustor. So, there is a pressure loss in the combustor which is given, and this is given to be 5%. So, that means this is 0.95 times P03 which works out to 2888 kilopascal. So, now we know P04 and T04. Right. We go to the next component, which is the HP turbine. So, at the HP turbine outlet, we obtain this expression by doing an energy balance for the HP turbine and the HP compressor. So, the HP turbine produces just enough work to run the HP compressor, and based on the energy balance we obtained that the exit temperature at the exit of the HP turbine is equal to T05 is equal to T04 minus 1 over eta mechanical times Cp over Cpg times T03 minus T02. So, I know all the quantities on the right hand side. If I substitute the values, I get T05 to be 1065 Kelvin. So, once I have T05, I can use the definition of the efficiency of the turbine, right. The efficiency of the turbine is defined like this: eta turbine is equal to T04 minus T05 divided by T04 minus T05s . So, I can calculate T05s from this expression. I know eta turbine also. Eta turbine is given to be 0.9. So, I can calculate T05s from this. Can you calculate this and tell me what it comes out to be? T05s is 1017 Kelvin. That is T05s. So, once I know T05s, I can calculate P05s using the isentropic relationship. So, if you remember, T05s divided by T05 is equal to raised to the power gamma g over gamma g minus 1, I am sorry, gamma minus 1 over gamma g minus 1 over gamma g. So, I can evaluate P05s from this equation. Did I do this correctly? Oh. Oh, I am sorry, this is T05s divided by T04, P05s divided by P04, yes. So, I can calculate P05s from this equation. Can you calculate and tell me what it is? .609 kilopascal. and you know that P05 is equal to P05S. So, this is going to be equal to 609 kilopascal. So, we have T05 and P05. Okay. Both 05 and 05s lie on the same isobar based on our definition of the isentropic efficiency for the turbine. Okay. So, that is the high pressure turbine. We now go to the low pressure turbine. So, at the exit of the low pressure turbine, we have the following equation. The low pressure turbine produces enough work to run the fan, which means that T06 is given as T05 times, T05 minus, remember the amount of mass flow rate through the fan is m dot, through the entire fan is m dot C plus m dot H. Okay. So, that is why we have this B plus 1 term here. Right, the fan handles the entire amount of mass flow rate, m dot H plus m dot C, and if you take that into account, then this is what we get for the expression for T06, and if you substitute the numbers, this comes out to be 815 Kelvin. So, I have T06, and from the expression for the isentropic efficiency of the turbine, I can do the I can write the following. So, this is the definition: T05 minus T06 divided by T05 minus T06S. So, I know T05, I know T06, efficiency of the turbine is also given. So, I can evaluate T06S from this expression. So, I get T06S to be 787 Kelvin. So, once I know T06S, I can use the isentropic relationship between 06S and 05 and write the following: T06S divided by T05 is equal to P06S divided by P05 raised to the power gamma G minus 1 divided by gamma G. So, from this I can calculate my P06S. Everything is known in this. So, I can calculate P06S. What do you get for P06S? Oh, I have 181 kilopascal. I have 181 kilopascal. and since P06 is equal to P06s, we have now completed this state also. So, this is 181 kilopascal. So, we have T06 and P06. So, now we need to move on to the hot nozzle, right. We have completed the calculation for the other components. Let us do the hot nozzle. So, at the hot nozzle exit, since I have P06, I can immediately evaluate the critical pressure, right. So, at the hot nozzle exit, the critical pressure PEH critical, we derived this expression before, this is equal to P06 times 1 minus 1 over eta nozzle times gamma g minus 1 over gamma g plus 1 raised to the power gamma g over gamma g minus 1. So, if I substitute the values for this value of P06, the critical pressure comes out to be 95.72 kilopascal and the ambient pressure is 100 kilopascal. Remember, the engine is on a static thrust stand. So, since the ambient pressure PA, which is equal to 100 kilopascal, is greater than the PEH critical for the hot nozzle, the hot nozzle is also the cold nozzle was also not choked, and for operation at sea level static pressure, you can see that the hot nozzle is also not choked. Therefore, this is also not choked, therefore, PEH is equal to PA is equal to 100 kilopascal. All right. Okay. So, what do we do next? So, as you can see from here, the hot nozzle is not choked, then PES equal to PE equal to ambient pressure. So, once I have PES, I can calculate TES from this expression, right. So, I can write PES for the hot nozzle divided by P06 is equal to TES for the hot nozzle divided by T06 to the power gamma g over gamma minus 1. So, from this I can calculate my TES for the hot nozzle. So, what do you get if you do this calculation? Okay, so gamma g over gamma g minus 1, okay, and what do you get for TESH? This is correct, is it? 703, okay. So, the efficiency of the nozzle, if you remember, is T06 minus TES divided by T06 minus TESH. So, from this I can calculate my TES. What do you get for TES? 706, that is what I also have. So this is 706 Kelvin. So once I have this, I can calculate the velocity. I am sorry, this is TEH, I am sorry, this is TEH. Yes, TEH, please change this. This is TEH, so I can calculate my TEH to be 706 Kelvin. So VEH can be calculated as 2 times CPG times T06 minus TEH, and if you substitute the numbers for this, what do you get for VEH? .500 meter per second, correct? So the thrust produced by the core engine, remember here also the pressure thrust is 0 because the nozzle is not choked, so PE is equal to P ambient. That means the pressure thrust is 0, so the thrust produced by the core engine is going to be m dot h times VEH minus VA, and VA is equal to 0, right, because the engine is on a thrust stand, static thrust stand, so VA is 0, and m dot h itself is nothing but m dot over B plus 1 times VEH. So if you substitute the numbers, we get the thrust produced by the core engine to be 63 kilonewtons. So the net thrust produced by the engine, which is the sum of the thrust produced by the fan and by the core engine, so the net thrust produced by the engine, which is the sum of the thrust produced by the fan and the core engine, comes out to be like this. So total thrust T is equal to thrust produced by the fan plus thrust produced by the core engine, and this comes out to be 166 kilonewton plus 63 kilonewton, which is equal to 229 kilonewtons, which encouragingly compares extremely well with the value reported by the manufacturer. So the manufacturer quotes static thrust value for this engine to be 233.6 kilonewtons. So this is from the manufacturer's website. So you can see that the calculations seem to be all right, we are getting reasonably good numbers. So now we can calculate the mass flow rate of fuel, and if you remember the mass flow rate of fuel, the expression for that, so this was the mass flow rate for fuel. So mf dot ideal is equal to mh dot times CPG T04 minus CP times T03 divided by H fuel minus CPG times T04. So please substitute the numbers and tell me what you get for this. 45,000 kilojoule per kilogram, that is the enthalpy of the fuel. Okay, we will continue this in the next class, finish it in the next class.